Welcome to the video Help with Physics Problems for Physics 1A. In this video we'll be covering homework set 5, part 3. This is questions in the first half of the oscillation section. For 1121 students that's questions 7 to 10. For 1131 students that's questions 8 to 12. Problem 7 for 1121 or 8 for 1131. In this body we have in this problem we have a body oscillating with simple harmonic motion. The equation for the simple harmonic motion is given by 6.0 cos 3 pi t plus pi on 3 meters. Okay, before we look at the questions, let's work out what the velocity and acceleration will be. So the velocity is equal to the derivative of this with time. So the derivative is 3 pi times 6, so that's 18.0 pi. And then this cos becomes a sine, and we have a negative sign. So 3 pi t plus pi on 3. Now to get the acceleration, we have to take the derivative again. And so we've got minus 18 pi times 3 pi. So doing that we get minus 54.0 pi squared cos 3 pi t plus pi on 3. Okay, now it tells us that t is equal to 2 seconds. And we're asked to A, calculate the displacement. Okay, this is easy, we just need to substitute in here. The only real trick is that if you're using the calculator, make sure, as these are in radians, that your calculator's in radians mode. To avoid that, let's not use the calculator. So we've got 6.0 cos 3 pi t, so that's 6 pi plus pi on 3. Okay, so this is just going around the circle 3 times, so it doesn't actually affect the final result. Pi on 3, let's just remember those trig identities. We've got pi on 3 or 60 degrees here, then this is 1, this is 2, this is root 3, and we've got pi on 6 up here. Okay, so we've got cos of pi on 3. Cos is adjacent over hypotenuse, so it's a half. So a half of 6 is equal to 3.0 meters, and that's the answer exactly. Part B says find the velocity at this time. So the velocity is equal to minus 18.0 pi sine 6 pi plus pi on 3. Once again, the 6 pi doesn't matter. That's going around the circle 3 times. So sine of pi on 3 is opposite over hypotenuse, so root 3 on 2. So this is minus 18.0 pi times root 3 on 2. So it's minus 9.0 pi. You could also solve it on the calculator if you wanted to. Oh, we left off the root 3. We need that root 3. Part C says, what's the acceleration? Okay, so substituting into this formula, we've got minus 54.0 pi squared cos 3 pi t, so that's 6 pi plus pi on 3. And now we've said that cos of this is a half, so a half of 54 is 27. So this is minus 27 pi squared, and that's meters per second. This one's meters per second. Okay, now part D says find the phase. The phase constant phi is this part here. So this is omega, this is the phase constant, so this is equal to pi on 3. That's the phase. Part E says find the frequency. We said this was omega, so omega is equal to 3 pi. Omega is 2 pi f, so 2 pi f is equal to 3 pi. Pi's cancel out, telling us f is equal to 3 on 2 or 1.5, and that's in hertz. And finally, part F says the period. The period is the inverse of the frequency, so in this case it's 2 on 3 seconds. Okay, now we're up to problem 8 for 1121 or 9 for 1131. In this problem we've got a ball going around a circular path. So the radius of this circle is 2.00 meters. and the velocity is given by 3.00 meters per second. Now part A says find the period and frequency of motion of the ball. Well, the period is just the distance over the time, which is how long it takes to go around the circle once. So the distance is the circumference, 2 pi r over the velocity. So that's 2 pi times 2 over the velocity, which is 3.00. Solving that on the calculator, we end up with 4.19 seconds. And then we're asked for the frequency, which is just equal to 1 over the period. So 1 over 4.19 gives us 0.239 Hertz. Part B says write an equation for the x component of the position of the ball as a function of time. Assume that the ball is on the positive x-axis at time 0. So it's moving here at t equals 0. It's got x is equal to 2.00 meters and y is equal to 0. Okay, so the formula for simple harmonic motion, x is equal to a cos omega t plus the phase constant. The amplitude in this case is the radius, so it's 2.00 cos, now omega t, this is 2 pi times 0.239. Now phi, when t equals 0, this should be equal to 2. So when t equals 0, we've got cos of 0 plus phi. 2 is equal to a cos, of 0 plus phi. Phi needs to be 0 so that this whole term can be 1. So this will be plus 0. So solving that, we've got 2.00 cos. Solving this on the calculator gives us 1.5 t. Okay, problem 9 for 1121 or 10 for 1131. In this problem we have a piston which is moving up and down. The period of the piston is given by 1.0 seconds, and we've got a block with mass, let's say m, placed on top of this piston. And in part A, it's asking us at what amplitude of motion will the block and the piston separate? Well, they're going to separate when this piston is accelerating downwards faster than the block. Okay, so the acceleration of the piston, because it's undergoing simple harmonic motion, is given by minus omega squared x, and so the maximum acceleration will obviously happen where x is the maximum. So when it's at its maximum height, it's going to be accelerating downwards, which is when it will lose contact, because when it's accelerating downwards, if the block isn't accelerating downwards as quickly, they will lose contact. So this is equal to omega squared a. Now the acceleration of the block is constant, it's just given by g. Well, that's the maximum acceleration. When it's in contact with the piston will stop it accelerating this much. Okay, so our limiting case is when these two are the same. So we've got omega squared a is equal to g, and so the amplitude is equal to g over omega squared, which is equal to g over, now we've got omega is equal to 2 pi f, which is 2 pi over t. So this is 4 pi squared times t. So solving this on the calculator, g is 9.8, t is 1. So putting that on the calculator, we get 0.25 meters. Okay, part B says if the piston has an amplitude, so now the amplitude is equal to 0.05 meters. It's 5 centimeters, which we can write as 0.05 meters. What is the maximum frequency with which this can oscillate and them still remain in contact? Well, once again, the maximum acceleration for the block is given by g, and for the piston it's given by omega squared a. And so when this exceeds this, then the piston's going to be accelerating down faster than the block and they will lose contact. So we have G is equal to omega squared A. We're trying to find F in this case. So G is equal to 4 pi squared F squared A, which tells us that F squared is equal to G over 4 pi squared A. Substituting in 9.8 over 4 pi squared times 0.05, and we get 4.9647. Taking the square root to find the frequency, and we get the frequency is 2.2 Hertz. So that's the answer to this question. Okay, this is problem 11, which is a 1131 only problem. In this problem, we're giving a spring. It has length L, and then we split this spring up into two parts, L1 and L2, such that L1 is equal to NL2, where n is an integer. We know just from this that L is equal to L1 plus L2, so we could write this if we wanted as NL2 plus L2, so that's n plus 1 L2. Now imagine applying a force F to stretch this spring. We're told this spring has a spring constant K, so it will extend an amount X such that F is equal to minus Kx. Now, as this spring is the same everywhere, we can split this extension up into the extension of length 1, x1, and the extension of length 2. And as it's constant everywhere, x1 would have to be equal to nx2. Okay, now let's consider a little point here where we're going to cut this spring. Now at this point, the spring 1 will be applying a force on spring 2 when it's stretched, pulling it back this way, and spring 2 will be applying a force on spring 1 back this way. So we know from Newton's third law that for every action there's an opposite and equal reaction. So mathematically we can write K1x1 is equal to K2x2. And we know that x1 is equal to nx2, so we can write this as K1 nx2. And then solving this part simultaneously, we have K2 over K1, cancelling off the x2's, is equal to n. Okay, now we need to try and work out what K1 and K2 are. Okay, now we know that if we apply a force F, we get minus Kx. And we can substitute in for x, that's x1 plus x2. And now what we can do is we can replace this x1 with k2 on k1 x2. So that we have x2 as a common factor. But k2 on k1 is just n, so this is minus k, n plus 1 x2. Now we can consider the force applied on this second part here. F2, by definition, would just be minus K2 x2. So now if we want to find out what K2 is, we can just equate these here. So we've got K2 is equal to Kn plus 1. And so that tells us what K2 is. K1 is equal to K2 on n, so we also know K1 is equal to Kn plus 1 on n. And so we've solved this problem. Okay, we're up to problem 10 for 1121 or problem 12 for 1131. In this problem we have a mass in simple harmonic motion with amplitude A, and we're asked what is the fraction of the kinetic energy component to the total energy when x is equal to a on 3. Well, the total energy is equal to the kinetic energy plus the potential energy. Now, because this is undergoing simple harmonic motion, when the spring is fully extended, there is no kinetic energy as the velocity at the extremes for simple harmonic motion is 0, so all the energy is in potential energy. So the total energy is equal to a half Ka squared. as that's how extended the spring is when the displacement is equal to the amplitude. Okay, now it says when x is equal to a on 3, what is the kinetic energy? Well, we can easily work out the potential energy. The potential energy is equal to a half k x squared, so a half k, and x is a on 3 squared, so that's equal to a half k a squared on 9. And so now we can work out the kinetic energy, which is equal to the total energy minus the potential energy. So the total is a half ka squared minus a half ka squared on 9, which is equal to 8/9 times a half ka squared, or 8/9 times, this is just the total energy. So at that point, the kinetic energy is 8/9 of the total energy.